right, in the last video we saw using all of our check matrices, using all of our elementary matrices, we ended up with a final result that we could multiply by A. So this product is called the check matrix. So the check matrix is the product of elementary matrices required to produce reduced row echelon form. Yeah, so here, E8 times E7, 6, 5, 4, 3, 2, 1, all of those together, that final product is called the check matrix, and we normally use W to denote it. So En minus 1, all the way down, all of our elementary matrices required. So like we saw up here, this product in this case, because we've created the identity matrix, this product also ends up being A inverse. So let's think about elementary matrices and how we can use them to find the inverse of a matrix. So if we've got some system and we're trying to find A inverse, well, so A times some matrix A inverse is equal to the identity matrix. This is similar to our AX equals B. So if we were going to solve this, one way that we would solve it is we would create the augmented matrix AB, and then we would do reduced row echelon form until we had the identity and our solution. So we're going to have a similar idea here. We're trying to find this A inverse. We don't know what it is. So we're going to create an augmented matrix AI. And then we're going to perform all of our row operations, and thinking about the elementary matrices required to do that, in the end, we're going to end up with the identity matrix here, and our identity matrix on the right from the augmented matrix is going to end up being our A inverse. That's going to end up being our solution. So let's look at how this would work. So I want to find the inverse here. So here's my matrix A, and I'm going to make an augmented matrix. With the identity. Okay. Remember, with my row operations, I'm doing the whole thing across my augmented matrix. So what I'm going to do first is I'm going to do leave row 1 the same. So leave row 1 the same. And then I'm going to do row 1 plus 2 row 2. So row 1 plus 2 row 2 is going to give me 0. Negative 17 plus 22 is 5. Negative 14 plus 11, negative 3. 2 row 2 plus row 1. 2 of row 2 plus row 1 is going to give me 1, 2, 0. Same as my elementary matrix. And now let's go with 0, 3, negative 2. I'm going to leave that one alone. Okay, so I could think about this as the elementary matrix, but I could also think about multiplying this row by 2 and adding it to this row. All right, now I'm going to try to get rid of my 3 down here. So I'm going to do 3 times row 2. Let me write this out. 3 row 2, and then let's say minus 5 row 3. I'm going to leave row 1 alone still. I'm going to leave row 2 alone for the time being. And now 3 row 2 minus 5 row 3. And then we will have negative 9 plus 10. That's really nice, is 1. And then 3 row 2, so 3, 6, minus 5 row 3. All right. I'm going to get rid of this 3. So row 2 plus 3 row 3. All right, row 2 plus 3 row 3. So 10. 2 plus 18 is 20. And then 0 minus 15. And that's really nice because when I divide by 5, all of that is going to simplify down. And then 3, 6, negative 5. So notice if I was still doing my check matrix, I would be finding my individual elementary matrices and multiplying them together to get this product. But performing the row operations each time means that I don't have to find the individual check matrices to find the product. I can just work along using my normal row operations. All right, so like I said, I'm going to divide by 5, so 1/5 row 2, 2, negative 17, 11, 1, 0, 0, 0, 1, 0, 2, 4, negative 3, 0, 0, 1, 3, 6, negative 5. All right, last one. So I want to get rid of my 17, get rid of my 11. So what I'm going to do is row 1 plus 17 row 2 minus 11 row 3. So that's going to give me 2, 0, 0, 0, 1, 0, 0, 0, 1. And now I want to be really careful with my math here. So I'm going to open up my calculator. Let's clear this out. So now I'm going to take my row 1 plus 17 row 2 minus 11 row 3. So 1 plus 17 times 2 minus 11 times 3. That gives me a 2. That's really nice. The zeros I don't need to worry about. 17 times 4 minus 11 times 6. Ooh, another 2. All right. And then negative 3 times 17 minus 11 times negative 5. And I end up with a 4. My other rows stay the same because I didn't do any row operations to them. Final step, I'm going to half my row 1. So 1, 0, 0, 1, 1, 2, 0, 1, 0, 2, 4, negative 3, 0, 0, 1, 3, 6, negative 5. All right, so now I've got my identity matrix and I have my A inverse. You always want to go back and check that you ended up with the correct matrix for your A inverse. So let's test it out. I'm going to just put it right next to it, and actually I'm going to put it in a different color. So let's put A inverse here. We had 1, 1, 2, and then 2, 4, negative 3, 3, 6, negative 5. All right, hopefully when we multiply, we're going to end up with our identity matrix. So 2, let's come back here, 2 minus 17 times 2 plus 3 times 11. Hopefully we get 1, indeed. Let's go with the next row and column, and we're going to end up with negative 17 plus 4 times 11 plus 6 times 3, and hopefully we get 0. Oh, something is wrong. Oh, perhaps because of the way I'm multiplying. So we should have this column times this row. So really I should have had 2 plus 4 times negative 17 plus 6 times 11. And we end up with 0. So again, keep checking it out. Hopefully we end up with the identity. 0, 0, 1. And that's how we can put together, how we can find the inverse without actually memorizing any formulas and just using row operations. So it's a really nice way to find an inverse, and you can find the inverse of any square matrix this way, assuming that the determinant is not 0, of course.